Hello everyone. So here I am with the part 4 of second chapter, which is mechanical properties of fluid. I hope you all have seen all the three parts regarding to mechanical properties of fluid, and this is the last part of our chapter. Last three parts have been covered 80% of the chapter, and this is the last part which deals with new concept, which is viscosity. So let's see what we are going to see in this part. So, following points will be covered in this part, which are first one, which is viscosity, that we are going to deal with it. Then coefficient of viscosity, Stokes law, which deals with the concept of viscosity itself. Terminal velocity, equation of continuity, Bernoulli equation, and application of Bernoulli equation. These all points will be covered in this part. So let's move towards first point, which is viscosity and coefficient of viscosity also. So here is the first point, which is viscosity. Okay, what is the compound definition? Viscosity is nothing but it is a property of fluid by virtue of which the relative motion between different layers of a fluid experiences a dragging force. This force is called viscous drag. Alright, so before moving towards this typical definition of viscosity, let's take two examples which will give you an idea about the viscosity. Alright, suppose we are considering two liquids. First liquid is water and second liquid is honey itself. Alright, so if I am throwing that water of glass of water on the floor, what happens to it? Water will flow all over the floor. Alright, if I consider honey, a glass of honey, and I throw that honey on the floor, what will happen to it? It will not flow as fast as compared to the water fluid. So why is it so? We can easily say honey is more viscous than water. That's why it is flowing all over the floor. So what happens exactly inside it? So if we consider water, example of water, what happens to water? All the molecules which are there inside water are moving with different velocities, right? That we have already seen. We are going to consider in this case fluid is having different layers, right? If we are throwing water on the floor or water on a table, what happens? Consider a table as a solid surface and on which water is spreading all over. So that water will be in different layers. First layer is moving with velocity 1. Then the second layer, which is above that, will be having different velocity. If we are going to consider it as V2, then the layer which is above that will be having a different velocity, maybe V3. So this increases. Alright, so exactly what happens, the molecules which are there inside the water are not opposing flow of water which is moving in forward direction or the direction, whatever direction they are getting to flow. They are not opposing that motion. But in case of honey, what happens? The molecules which are there inside honey are trying to oppose the motion. They are not allowing another particle to move over one another. So in that case, we are saying that honey is more viscous than water. Alright. So this is nothing but viscosity. So let's see what is velocity gradient then. The rate of change, that is dV, with distance dx, as we have seen, we are considering table as a solid surface and there will be different layers of water and honey itself. If first layer is having velocity v, second is v2, third is v3, whatever, then what will be the rate of change of velocity? It will be different according to the length from the solid surface. So velocity gradient is nothing but change in velocity with distance, which is dv by dx is nothing but velocity gradient. Okay, so Newton have given us a formula which is F is viscous force. Alright. So F is directly proportional to A into dV by dx, where A is the area of the layer on which fluid is flowing. Alright. So F is directly proportional to A dV by dx, where dV by dx is nothing but velocity gradient. To remove proportionality sign, we have kept a constant term which is eta. So F is equal to eta A dV by dx, where eta is constant and it is called coefficient of viscosity of the liquid. The liquid may be water, may be honey, may be oil, may be kerosene. It may be anything. F is equal to eta A dV by dx. Now coefficient of viscosity can be defined as what? It is defined as viscous force per unit area per unit velocity gradient, because according to this formula, which is F is equal to eta A dV by dx, what will be eta? Eta will be F divided by this A dV by dx. So it is force per unit area per unit velocity gradient. So you can calculate dimensions as well as unit for viscosity also, or coefficient of viscosity. You can find out that is nothing but Newton second per meter square as in SI unit. Alright, so this is nothing but viscosity. Viscosity is nothing but resistive force. Alright, and we have seen another new word which is viscous drag. Viscous drag is nothing but air resistance, which is there inside the fluid or there inside the liquid. So this is all about viscosity. Right? So let's move toward our next point, which is Stokes law. In this law, we are going to consider an example of metal bulb and liquid. Consider a glass of water, and we are going to throw an metal bulb inside a glass of water. What will happen to it? That the metal bulb will move inside the liquid. If I change the liquid from water to oil, by how much amount that metal bulb will flow inside it, the velocity and the force will depend on in which fluid it is moving. Alright, so it is depend directly on viscosity, viscous force of that fluid. So that is given by Stokes law. So Stokes law says that viscous force, which is Fv, acting on a small sphere which is falling through that viscous medium, is directly proportional to radius of the sphere, which is r, its velocity v through the fluid, and viscosity eta of the fluid. Obviously, these all terms are necessary when any metal bulb is moving inside a fluid. Its radius should be considered, the velocity with which it is moving it is considered, and eta, which is coefficient of viscosity, should be considered. This is Stokes law. According to law, Fv is directly proportional to eta Rv. Viscous force is directly proportional to eta, coefficient of viscosity, r, radius of the sphere which is moving inside the viscous medium, and v, that is velocity of that sphere. Empirically, the constant term is 6 pi. So we are getting Fc is equal to 6 pi eta Rv. So this is Stokes law. What it gives when any metal ball is thrown inside a liquid or thrown inside a fluid, it will move downwards inside the fluid, and it is due to viscous force, it is due to radius of that sphere, and velocity with which it is moving. It will differ from material of the fluid. If I am going to consider water fluid, velocity will be greater rather than we are considering oil or honey. It will be different. So that depends on the viscous force. So this is all about Stokes law. So our next term is the terminal velocity. before going to learn this phenomena, which is terminal velocity, we are going to consider same example which we have seen in the last slide, which was Stokes' law. In that case, we have considered a spherical body which is moving inside a fluid. What happens to that body and what happens to that fluid? The fluid exerts a force on the body, which is viscous force, and a spherical body which is moving inside the fluid is having many kind of force which is acting on it. So we are going to consider all the forces and we are going to apply that Stokes law in this case, and we are getting the term which is terminal velocity. So let's move towards this point by considering that the same example. You can see over here the diagram in which you can see a container is there which is having a viscous fluid inside it, and the spherical body is moving inside it. So as we throw any body inside a fluid, and a force it is in upward direction also creates. As the force in downward direction due to weight of the spherical body happens, at the same time it creates some upward force which is nothing but a thrust, or say as buoyant force. So there are three forces which are acting in this case. First force is viscous force, which is due to the fluid which is inside the container, and it will be changing. It changes with the layer of the fluid. So if it goes on changing as the ball or the spherical body moving inside it. And second force which is acting in this case is gravitational force, which is nothing but the weight of the spherical body which is directing downwards. And as we have discussed buoyant force, it is a thrust. It is nothing but Fu. We are going to denote that as Fu. So it is directed upward. So by considering all the three forces, what will be the net downward force? Net downward force is nothing but small f, and it is given by the equation Fg minus Fv per u. As Fg is given by the weight of the ball, so Fg will be positive in the sense, and Fu and Fv, Fv is nothing but viscous force and Fu is nothing but a thrust. So that force is in a single bracket, Fu plus Fv, and it should be in negative because they both are in opposite direction. So it is Fg minus Fv plus Fu. It is responsible for the initial increase in the velocity. Now at some point we are going to consider F is at 0. Net force will be 0. So what will happen to that equation? That equation will become Fg is equal to Fv plus Fu. So in this case, Fg, which is gravitational force, which is due to weight of the spherical body, will be obviously constant. Viscous force, which is directing upward, but it will be goes on changing from layer to layer. What will be Fu? Fu is a pressure which is beyond force, is also constant term. So by considering this equation, we can say only F increases with increase in velocity. But after that, by considering F is equal to 0, the downward velocity remains constant. This constant downward velocity is called as terminal velocity. The downward velocity which remains constant after condition F is equal to 0, that constant downward velocity is called as terminal velocity. Now obviously F becomes constant. As we have already discussed, F is constant because it is viscous force, and as F is again constant and F is again constant, so if between three terms, if it becomes constant terms, third will be constant. So Fp becomes constant now and onwards. So let's see what happens next. What we get the equation according to this. Now to derive the another equation for it, we have to consider mass of the spherical body, density of the spherical body, density of the fluid in which the spherical body is moving. That all the terms we are going to consider. So let's consider m as the mass of a sphere, sigma as density of the sphere, G as the gravitational constant, R as the radius of the sphere, V as the velocity of the sphere itself, and sigma is the density of the fluid, density of the liquid in which the spherical bob is moving. So have a look in the diagram again. From that diagram you can say total downward force. Total downward force is equal to total upward force. For balancing condition, both the forces should be balanced. Now, downward force is nothing but gravitational force, which is m into g, which is weight. What will be m? According to density, m will be rho into v, and rho is the density and v is the volume. Volume of what? Volume of sphere. Volume of sphere is 4/3 pi r cube. So instead of m, we are going to put 4/3 pi r cube, and g will be as it is a gravitational constant. And what will be upward force? Upward force is viscous force and buoyant force due to the medium. So viscous force is nothing but, according to Stokes' law, it is 6 pi eta RV. We have derived it. We have seen the Stokes' law in the previous slide. So viscous force is 6 pi eta RV, and buoyant force will be same as that of the 4/3 pi r cube rho g. But in this case, we are going to consider density of the fluid. So density of the fluid is sigma. So that will be 4/3 pi r cube sigma into g. So you can get the equation 4/3 pi r cube rho into g is equal to 6 pi eta rv plus 4/3 pi r cube sigma into g. Alright. So by taking 6 pi rho rv on another side and 4/3 pi r cube rho g and 4/3 pi r cube sigma g in another side, we can get the next equation, which is 6 pi eta rv is equal to 4/3 pi r cube sigma g minus 6 4/3 pi r cube sigma g. Alright. So what you can say in the next term, in the next equation, 4/3 pi r cube and g, all terms are constant. So you can take the terms outside the bracket, and inside the bracket what you can get? You can get rho minus sigma only. So you are getting 6 pi eta rv is equal to 4/3 pi r cube g in bracket sigma minus rho minus sigma. Sorry, rho minus sigma. So we are going to find out the value for terminal velocity. So we are going to find out. So by taking 6 pi eta r on another side, we can get value for v. So what will be v then? V will be 4/3 pi r cube g rho minus sigma into 1 divided by 6 pi eta r. By cancelling out the same terms, the terms which are common in it, we are going to cancel it out and we are getting value for v. Value for v is 2/9 r square g rho minus sigma divided by eta. So this is nothing but terminal velocity, and we can get the value for eta also. So eta will be 2/9 r square rho minus sigma g divided by b. So this is value for eta, which is coefficient of viscosity, and b as terminal velocity. So this is all about terminal velocity. So what you have seen in terminal velocity, a spherical body is moving inside the fluid, which is having some viscous force, which is having a thrust, which is having gravitational force inside it. We have balancing the equation by total downward force is equal to total upward force. The total upward force is given by buoyant force as well as viscous force, and the viscous force is given by Stokes' law. So by equating the equations, we are getting the final value v and final value for eta. So this is all about terminal velocity. So let's move to our next topic, which is equation of continuity. Now, equation of continuity will give you the idea about how the fluid flows through any object, through any pipe or through any area, how it flows and how it is conserved. That we are going to say in this. Alright. For the equation, we have to consider the fluid is incomprehensible. So what is the meaning of exactly incomprehensible? Incomprehensible is nothing but the fluid which is having same volume. Whenever you are applying external pressure, still the volume will be same. That is nothing but comprehensibility of a fluid. Right? So let us consider example of river. When we see the water is flowing through river, when river having wider area, what happens to the water? Does it flow faster or slower? I'm repeating again. If I am considering river and water inside the river, if the area or it has a wider area to travel for the water to travel to the wider area through the wider section, what happens to speed of the water inside the river? Obviously it will slow down. Why? Because it has the larger area to travel. So when wider area is in consideration, fluid which is flowing through it will be slowed down. Speed will be slowed down. And if it is having narrower area, narrower section, the fluid which is inside it will move faster because it is having very lesser area. So it will move faster as compared to the wider section. Unless and until it is incomprehensible. Alright. So let's study about this. To study this phenomena, we have to remind something, and that is nothing but flow tube, flow line that we have already seen in part 3. Alright. So what we have seen in flow tube and flow line. Flow line is nothing but it is the individual path of individual particles moving ahead, moving fluid. If we consider a moving fluid, the individual path of particles is flow line, and if we consider a bunch of flow lines, that will be a flow tube. And the flow tube is bounded by an imaginary wall. And if we consider a flow is steady, that fluid cannot pass or cannot cross the wall of the flow tube. And streamline the steady flow, and now laminar flow and streamline flow are one and the same flow which are steady. Alright, so we are going to consider the flow as incomprehensible. What is incomprehensible? Volume of that fluid is constant. Alright, so let's move toward the equation, mathematical equation of that. So have a look in the diagram. Let's see, there are two parts. That is the flow tube. There are two parts. First part is EFGH and second part is PQRS. EFGH is having area A1 and PQRS is having area A2. You directly says that A1 is greater than A2 because PQRS is having narrower section, narrower area, and EFGH is having wider area. As we had said that the fluid is flowing to any object, to any pipe or to any flow tube, it will move or it will having velocity larger at wide narrower section and slower speed will be low at wide section. So at PQRS speed is V2 and at EFGH speed is V1. So as it is moving from one part to another part, as it is flowing from one part to another or one point to another point, it will be in some time t. So we are going to consider that time delta t. So how much distance is covered by that fluid from one place to another place? At PQRS it is V2 into delta t for cross section area A2. When it fluid is moving through PQRS of area A2, velocity V2 and time delta t, and when it is moving towards EFGH of area A1, velocity V1 and in time delta t. So distance which is travelled by the fluid at PQRS will be velocity in time, so that will be V2 into delta t, and similarly EFGH will be V1 into delta t. This is okay. So let's move to another point. So if the amount of water is flowing through this flow tube, how much amount will come out from that flow tube? Obviously, the same amount will come out, because as we have said, it is a steady flow and it is incomprehensible, because the fluid cannot come out and no fluid will come inside the flow tube. So the mass which is coming inside, mass of the water which is coming inside the flow tube will remain same. It is coming out. So this is nothing but conservation law. So matter neither created nor destroyed within this tube enclosed between A1 and A2, area A1 and A2. So what we have seen, mass of the matter. Here matter is fluid. If we consider it is fluid is water, then mass of water will be same. When it is entering the section A1, equal mass of fluid should leave the section A2. Alright? And the speed we have V1 and V2 are the speeds. What will be mass at point A? According to the definition of density, rho is equal to mass upon volume, right? So by using the equation, we get mass at A is nothing but rho A1 V1 into delta T. So volume is nothing but A1 into V1 into delta T. How we get this? As we said that if the fluid is moving from one point to another point, if we consider at point A is but area, it is moving through area N with velocity V1 and in time delta T. So volume of that will be area into distance travelled. So how much distance is travelled? Distance travelled is nothing but velocity into time. So we got volume as A1 V1 delta T. Thus mass at A is rho A1 V1 delta T. Similarly, you can say mass at B will be rho A2 V2 delta T. Rho must be same because density is same. Same liquid flowing to the flow tube from point A to B. So rho must be same. So according to the conservation, mass of fluid in section EFGH should be equal to mass of fluid in section BQRS. So mass at A is rho A1 V1 delta T is equal to rho A2 V2 delta T. So we get cancelled. Delta T will get cancelled. You are getting equation as A1 V1 is equal to A2 V2, or you can say A V is constant. So this is nothing but equation of continuity. Alright. By considering the equation of continuity, which is equal to constant, AV is nothing but volume rate of change of that fluid. So if you consider AV as dV by dt, the quantity dV by dt is the volume of fluid per unit time which is passing through any cross section area of the tube of flow. That is called as volume flux. Similarly, if you multiply dV by dt by rho, so we are getting rho dV by dt. Rho into volume will be what? M obviously. So you are getting rho dV by dt is equal to dV by dt. So dN by dt is called as mass flux. Okay. Now we have already derived the equation, right? So in case of continuity equation, we have to say that the fluid is incomparable and it is steady flow only. We have to consider the fluid is steady and incomparable. Then only then the equation of continuity is correct. So which is nothing but A1 V1 is equal to A2 V2, or we can say A is equal to constant. The amount of water which is flowing from point A will be same amount when it is going out. Mass is same, it is incomprehensible, and it is steady flow. Volume is same as we have said, it is incomprehensible. Alright, so this is nothing equation of continuity. Now we are moving towards the next, which is Bernoulli equation, which deals with the same, but we are going to consider a new point inside it, which is pressure. So let's move towards the next point. So here is the advanced part of continuity, which is Bernoulli's equation. In Bernoulli's equation, we are going to consider the law of continuity, but in the advanced part which is we are going to consider one new term which is pressure, and the previous term is work energy theorem, because it is nothing but the application of work energy theorem. So let's see what is that. We are going to consider the same example of water flowing through river. What happens to the water when it's flowing through river? When narrower comes, the speed goes on increases. And when the wider region comes, the speed will slows down. Why is it so? Because in the wider region, the space to move forward, the molecule will be higher. So they will slow down the speed. But what happens to the pressure? So as we say, speed is higher. So the internal pressure will be highest at narrower and lowest at wider. Does it so because the speed is higher? So we might think like that. The pressure at narrower region is highest because at narrower speed is highest. But it is very wrong. It is the wrong statement. Scientist Bernoulli had done the experiment and he had proved that the speed of fluid in narrow region increases, but the internal pressure of fluid in the same region decreases. The pressure will decrease at the narrower and it will increase at the wider. So let's see how does it prove. Does it prove that? And the most important concept in this that we are going to study is this is nothing but the law of work energy theorem. So have you reminded what is work energy theorem? We have studied in energy chapter. Work and energy are interrelated. Work done is given by change in kinetic energy and change in potential energy. So this is the relation between work and energy. So in this case, we are getting the same equation. So let's move forward to get that, to derive that. So have a look at the diagram. By using the diagram, we are going to prove the relation between work and energy, and we are going to derive the Bernoulli equation, which says that it pressure at narrower is decreases and pressure at wider increases. So let's move towards our next derivation. See diagram. In diagram you can see the flow tube again. In that flow tube, fluid is going to flow. The fluid is steady. Fluid is incompressible, so the volume will be same inside it. The amount which is going inside the flow tube will same amount to come out. Okay. So see here, figure shows that the ideal fluid through a tube varying cross sections and height. Height is different and area of cross section at two different points are different. We are going to consider two different points. The first point is P and second point is R. Alright, so at P point area is A1, height is H1, the distance covered by the fluid is D1, velocity is V1. What will be force then? Force will be pressure in area. That will be A1 into P1. Then when the fluid flows towards point R, at point R, area is A2, velocity is V2, distance traveled is D2, and force is P2. Now what happens in this equation? You can see at point R, it tries to resist the displacement of the fluid. So it is coming inside. As the force at point P is coming inside, and at point R, force is again coming inside, which is P2A2. Alright, so let's see what happens. As the denotations P1, P2, A1, A2, P1, P2, and P1, P2 that we have already discussed. So we are not going towards point number 4, 5, 6, 7. Let's move toward point 8. What will be the forces at point P and R? As according to definition of pressure, pressure is F upon A. So what will be F? F will be P into A. So here we are getting forces as P1, A1 and P2, A2. Alright. So what will be dV? What is dV? dV is nothing but volume. Volume will be what? Same, because it is incompressible. Alright. So volume will be area into distance traveled. So it is A1 D1 and A2 D2. But as volume is same, you can say dV as A1 D1 is equal to A2 D2. So this is all about dV. Then what you can see in this equation, or what you are going to consider in this equation, only non-gravitational force will does the work on this, because it is due to pressure of the surrounding. No other force will act on it. Only pressure. We are going to consider the pressure term. Alright. So W, work done by definition, it is force and displacement. What is force P1 into A1? What is the displacement at point A or at point P? It is at point R, it is into. So W is equal to P1 and A1 minus P2 A2. What is the negative sign indicate? As we have said, it at point R, it opposes the displacement of the fluid. So it gives you a negative sign. So W is nothing but P1 A1 D1 minus P2 A2 T2. Now what is A1 D1 and what is A2 D2? 8.8. We have said it is nothing but dV. So we are going to put the value instead of 71 and 8 dV, we are going to put dV. So you are getting W as P1 dV minus P2 dV. We can take dV outside as it is common in both terms. So you are getting W is equal to P1 minus P2 into dV. So it is completely depending on the pressure and not another term. Right? But according to what theorem, what should be W? Should be change in kinetic energy and plus change in potential energy. So let's move forward to find out what is kinetic energy, or what will be the change in kinetic energy and what will be change in potential energy. We have to consider this diagram in the next slide also. Okay, so we have to consider this, and I'm moving forward to the next slide to find out kinetic energy and potential energy. So let's move towards the next slide. Kinetic energy will be what? At point P, it will be half mv square. At point Q, it will be at point, it will be half mv square itself, but m1 v1 square and m2 v2 square, or m1 m2 will be same or what? Yes, mass will be same. Mass is nothing but rho into volume. Yes, rho, and rho is nothing but mass divided by volume. Mass will be rho into v. We are going to consider instead of m, we are going to put rho into a1 d1 and rho into a2 d2. Right? So change in kinetic energy will be kinetic energy at point R minus kinetic energy at point P. So let's consider what is that. Kinetic energy at point R is half mv square, mv2 square. Right? Instead of m, we are going to put rho a2 d2 into v2 square. Alright, and at point P, it is rho a1 d1 d1 square, half obviously. So delta kinetic energy, change in kinetic energy is equal to half rho a2 d2 v2 square minus half rho a1 d1 d1 square. So what is common in both the terms? Half is common, half is same, rho is same, and we have seen in point number 8, which is a1 d1 and a2 d2 is the same because it's dv. So we can take common of the same term and we will see what happens to the equation. So we are getting kinetic energy, or change in kinetic energy, as half rho dv in bracket v2 square minus v1 square. Alright, so this is nothing but change in kinetic energy. Now what we are going to say is change in potential energy. So basically what is potential energy? It is mgh, where m is mass, g is gravity, and h is the height. So what is m over here? M at P and m at R is nothing but rho a1 d1 and rho a2 d2. So let's see. So at the beginning, gravitational potential energy of mass m is mgh1. Instead of m, rho a1 d1 and a2 d2 are same, which is dv. So we are going to put instead of a1 d1 dv itself. So we are getting potential energy as mgh1 is equal to rho dv. G will be as it is, h1 will be as it is. we are just going to put rho into dV instead of m. At the end, what will happen to the potential energy? It will be mgh2. So again, rho dV g h2. So what will be net change in gravitational potential energy? That will be delta P potential energy. P is rho dV gh2 minus rho dV gh1. So what is common in both the terms? Rho is common, dV is common, and obviously G is common. So what remains in the bracket? That is h2 minus h1. That is the difference in height itself. So delta P1 is rho dV G into bracket h2 minus h1. So what will be W then? W will be adding of both the terms. It is kinetic energy, potential energy. So we are getting half rho dV into bracket V1 minus V2 square plus rho dV G into bracket h2 minus h1. So this is the last equation, and this equation gives you Bernoulli's equation. It states that the burden per unit volume of the fluid by surrounding fluid is equal to sum of the kinetic and potential energy per volume that occurs during the fluid. Alright, by considering that equation, we can write it is again in another form, which is P1 plus half rho V1 square plus rho G H1. So I have said P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. All the first term, which are related to P, is on another side, and all the terms that are related to it are on the another side. So you're getting this equation. So we can directly say that P plus half rho V square plus rho G H is equal to constant. So this is nothing but the Bernoulli's equation. So now we are going to see what is the application. That will be the class book for you all. You are going to go through the textbook and you are going to see what is exactly the Bernoulli's equation and what happens when it is applied to our daily life examples. Alright, so you are going to look at the textbook and you are going to see what are the applications of Bernoulli equation. I have given you the idea about it and you are going to see that textbook. It is very easier, so you will come to know how it is. So just have a look in the textbook and you will come to know how it is, how the Bernoulli equation is being applied. Alright, so these are some applications of Bernoulli equation. First is you speed of a flux, working of an atomizer, lifting up of an airplane, blowing off roofs by storm winds. These all examples deal with Bernoulli equation. So please look at all the applications, and if you have any query, if you have any doubt, do comment. I'll answer your query and I will solve all of your doubts. So please go through this part and have a look. Okay, thank you so much for having a look at part 4. And this is the chapter of mechanical properties of fluid. In this chapter, we have seen many phenomena such as we have seen this, which is motion of fluid, Bernoulli equation, then Torricelli equation we have seen, Stokes law we have seen. That means the phenomena which deals with pressure, with fluid, motion of fluid, viscosity we have seen. We have seen surface tension, application of that, what factor depends on that, all the concepts which are being covered in this chapter, which is mechanical properties of fluid, all the properties that we have seen. Alright, so we are going to study the numericals, we are going to solve the numericals in this chapter. In the next part, we'll see all the numericals. Most of the numericals I will try to cover, but rest you have to cover. Alright, so this is about the chapter, this ends the chapter. Thank you so much. Please have a look at all the parts that covers all the theory of mechanical properties of fluid, and do comment and ask me queries. Thank you so much.